So today, the InChI is a way of naming molecules, and naming molecules raises all sorts of questions of identity and of diversity, and of the importance of each individual molecule. So we're going to be as much philosophical as chemical. A fundamental question is, what is a molecule? We need to be able to answer that in order to work out how to name them. And naming molecules is going to be hard work because there are so many of them. There are about 10 to the 100 small molecules which might interest us. There are only 10 to the 10 people in the world. So if we divided them out evenly amongst everyone in the world, people would have about 10 to the 100 each, which is a lot of names to think of, far more than naming every star in the sky, or every grain of sand on the beach, or every grain of sand on every beach on the world, or every grain of sand on every beach on every world throughout the universe. So thinking of names for molecules in a way which is reliable and understandable and useful is really a very serious challenge. And the InChI is one way to do this. So the InChI can name molecules in lots of different ways. It is now the beginning of a a much larger structure of systems. But I'm going to begin by explaining the thing at the center of this, this wheel, the InChI itself. With this, we can name molecules. We can then build out to issues of stereochemistry and tautomers and organometallics, and build more and more layers, extending the use of the InChI, so that we can encompass as much of chemistry as we possibly can. So for the moment, just look in the center of this wheel, and we'll come back to the outer layers as I go on. So we can use the InChI to name molecules, and we can use it to name molecules as a line of text. So if we choose a random molecule, which I've drawn here, well, this has a name. Its name is 1,4-chlorophenolethan-1-one, which suggests perhaps that of it is just decoration to these two carbons. Of course, if you're an American, then you might prefer to call it 4-chloroacetophenone, which suggests that it's basically this molecule with a chlorine attached to it. So both of these are perfectly sensible names, but they're different names. So if you're looking for some 4-chloroacetophenone, then you might not realize that 1,4-chlorophenolethan-1-one is actually the stuff you want. And that's a real problem. We want to have one name for each molecule. We want to have one molecule for each name. Now, one way around this is to have a registry system. And one of the most important registry systems comes from the American Chemical Society, the Chemical Abstract Service, or CAS. And if you ask CAS what's the name of this molecule, then CAS will tell you 99-91-2. This is a number which they've assigned to it. Someone gave them the structure some time ago. They said, this is a number, we'll make sure no one else, we'll make sure we don't assign this number to any other molecule. So CAS numbers ought to be unique. Usually, there is one CAS number for any one molecule, and there is only one molecule for every CAS number. There are a few exceptions to this. But this system only works because the Chemical Abstract Service exists. You can only get CAS numbers by interacting with the Chemical Abstract Service. So if you're inventing molecules and not in contact with Columbus, Ohio, this can be quite tricky. It would be good to have ways of naming molecules as line notations which don't require communication with a global authority. And there are lots of ways of doing that too. One of the older ones is called Vice-Versa line notation, which encodes this structure in a really very compact way. If I were to say to the right people, GR-DV1, then they'd immediately think, 1,4-chlorophenolethan-1-one, and be able to relate it to this structure. The number of people who can do this is now rather small. Vice-versa line notation was one of the first of the line notations, but it's no longer as widely used as various others. An extremely widely used line notation are smiles. A smiles, or a smile string, is a way of writing down a molecular structure as a string of letters, and I've written down the smile string for this molecule. It's more or less human readable. So C means carbon, CC means two carbons joined to each other, So like the IUPAC name, we're beginning with 2 carbons joined to each other at the top right-hand corner of the molecule. Then a bracket means a branch, and the bit between these brackets means the rest of the chain. So we do this carbon, then we go around this ring, stopping for a moment at chlorine, then we come back to where we were before, and as a sort of afterthought, we put the oxygen in. So with a bit of practice, you can look at a structure like this and write down a smile string, and with a bit more practice, you can look at a smile string and translate it into a structure. And that's very useful, but why begin at the carbon here? Mightn't it be more fun to begin at the chlorine here? Or you might think, let's begin at this carbon and then go to this carbon, then do a quick detour to the oxygen, and then go around the rest of the ring. And you can do that in lots of different orders. You can write down lots of different smile strings which relate to this molecule, and all of those smile strings are correct. So whilst a smile string will relate to one molecule might have many different smile strings which relate to it. So this is really useful, but if you write down a smile string of a molecule, someone else might be using a different smile string for the same molecule. It's really quite difficult to search for this sort of thing. The InChI is an alternative way of addressing the same issue. It's a bit harder to understand, and I'll come back to that in a few minutes. But the key idea about an InChI is that one molecule has one InChI, and one InChI relates only to one molecule. So for this particular structure, there's only one InChI which is correct, and that's the one I've written down here. And if you have this InChI, there's only one molecule which relates to it, which is this. Now, you might need computers to help you to do the conversion, but the computers which do this, computer programs are publicly available. This is all fairly straightforward. InChI strings can be extremely long. There is also something called an InChI key, and I'll explain this in more detail later, which is a way of packing an InChI into a fixed string length, which might make it easier to do some searching. So we can take a two-dimensional structure and turn it into a string of letters in quite a number of different ways. The smiles and the InChI and InChI key are all structure-based. We just need to know the structure. Beginning with the structure, we should be able to generate them. The InChI, at least, is unique and canonicalizable. There's only one and exactly one for each structure. The algorithm which produces it is open source, and the ownership is in the public domain. So you can work out exactly how this algorithm works, and that's a very useful feature of the structure. So to look at another example, let's think about benzene. Benzene we can draw like this. Actually, we can draw it in a number of other ways too. It also has a Cas number. Its Cas number is 71432, a smaller Cas number than acetophenone, which suggests correctly that it was discovered first and chemical abstracts registered it first. And the time at which the molecule was registered with chemical abstracts might be an interesting thing to know, but it isn't perhaps of fundamental significance. We can write down the smile strings for this. We can do it in a number of different ways. Two of the main ways are like this. We can write carbons with double bonds to show it's an aromatic system, or we can say that the carbons are aromatic and the convention is to write them as a small c. So here are two different smile strings, both of which are really good representations of benzene. Or we can write it as an InChI. This is the way that the InChI works for benzene. Notice at the beginning, C6H6, this is the molecular formula for benzene. And then we chase around the connectivity. And if we want to interpret this, if this is atom 1, it's next to atom 2, which is next to atom 4, which is next to atom 6, which is next to atom 5, which is next to atom 3, this may seem slightly illogical, but this is the only correct InChI. If you're writing an InChI, you have to number it in this order. And that turns out to be terribly important. And then if the InChI is inconveniently long, we can abbreviate it as the InChI key. For this particular molecule, the InChI key is longer than the InChI, but in the majority of cases, the InChI key will be shorter. So each of these different ways of representing benzene have different advantages. So the name benzene, of course, is pronounceable, so easy to say. The Cas number, well, that's proprietary, so it's really useful, but you can only get it through Cas. SMILES are human constructible, human readable pretty much, but they're not unique. Whereas the InChI is canonical. There's only one InChI which relates to this structure, and it is readable just about by humans. You have to be fairly dedicated, much easier to use a computer to turn it into a structure. And then the InChI key, well, this really is undecodable, or more or less undecodable. It's divided into a string of letters, a hyphen, a second string of letters. The second string of letters in this case is ufa-oisa, which is the same as it was for chloroacetophenone. So ufa-oisa is understandable, just about, but the InChI key essentially is undecodable. Once you have it, it's a hash of the structure, useful for searching, not so useful for decoding. And then the two-dimensional structure. Well, this looks beautiful, perhaps. By drawing it, you are drawing it in a particular orientation. So this is a correct way of drawing benzene. This is also a correct way of drawing benzene. This orientation can be somewhat confusing, but it's all ways of representing benzene. But we want, in order to search, in order to use this effectively, we would like to have just one way of representing benzene. So how does the InChI work? The InChI provides one way of representing molecules and is coordinated by the InChI Trust, which is a UK charity which provides funding for the development of the InChI. The InChI began about 20 years ago, and it was at the beginning a number of key people were involved. One of them was Steve Heller, who's still the chair of the IUPAC subcommittee and the chief driver for the development of the InChI. He worked for NIST, the National Institute of Standards and Technology at the time, having been involved with MDL, and so an expert on encoding molecules for pharmaceutical companies. Steve Stein worked at the NIST as well. Alan McNaught was the key person within IUPAC to drive the InChI forward, as well as being employed by the Royal Society of Chemistry. So his expertise with both IUPAC and the Royal Society of Chemistry enabled the InChI to take off. And Dmitry Cherkovskoy was the person who actually wrote the program. So his enormous contribution was to write the algorithm which created the InChI in the first place. And these people together had an extraordinary combination of skills and talents. And Dmitry was and is a mass spectrometrist. So in addressing the key question, what is a molecule? This is actually rather a difficult question. When does a molecule stop being a molecule? Are there things which are not one molecule but several molecules? Or should you treat ensembles of molecules which are linked together as a single molecule? How big can a molecule be before you treat it in different ways? All of these are difficult questions, but Dmitry had a clear answer to this because molecules are things of which you can have mass spectra. So beginning with NIST's database of mass spectrometry, he was able to develop an algorithm which encoded them as strings, as InChIs. And by defining molecules in this way, which is defensible, but possibly not the only way you could define molecules, made it possible to develop the InChI. So the InChI is now run by the InChI Trust, but it's also guided by IUPAC, the International Union of Pure and Applied Chemistry, which has an InChI subcommittee, of which Steve Heller is the chair, and I'm currently the secretary. So if you are interested in what IUPAC is doing with InChI, then contacting Steve or contacting me would be a way of seeing how the InChI is currently developing. So that's the structure of the InChI. Why is it useful? Well, here's a molecule which a colleague of mine, Dominic Wright, made recently, and Sanha Lee in my group did some calculations on. This is a really rather beautiful molecule, which looks, here we're showing some of its orbitals, and you can have a clear sense of what the molecule is like, but it's not an easy molecule to write down the name. This is its structure, and what it was called in the paper is an inorganic macrocycle, or we could call it a pentameric cyclodiphosphosane macrocycle. These are ways of describing it. They're not unique names. usually when I'm trying to make a name for a paper nowadays, I just draw it into ChemDraw and do the structure to name feature. If you do that with this molecule, then ChemDraw helpfully tells you a name could not be generated for this structure. I'm sure there is a IUPAC name for this structure, but it's not one which is easily accessible. It is possible, however, to generate a SMILES representation of this molecule, and this is the one that you get from ChemDraw. There'll be many other SMILES representations of this molecule. Oh, and I noticed that the reference at the bottom of the screen, my computer was helping me with this, and it noticed that Alex, who was the person who made the molecule, his name begins with A. Therefore, if the first line begins with A, the second line should begin with B. This is obviously a list. So A, J, plagiar, B, Angevantecami, C, the digital object identifier. The computer was helpfully adding extra and incorrect information into the simpler reference which I'd given it. This is a problem for references. It's also potentially a problem for molecules. You draw a molecule, what's the information that you're putting in? Are there several different, different levels of understanding which the computer may or may not encode in a SMILE string or in an InChI? So this particular molecule does actually have the shape that I've drawn here, with the hydrogens all pointing into the middle. Or the hydrogens attached to nitrogen, all pointing into the middle. Sorry. But you could imagine other conformations as well. The InChI does not try to encode that. The InChI just gives you the connectivity. It doesn't try to encode or remember the three-dimensional structure of the molecule. So we can get an InChI for a molecule of this level of complexity, and it's now really rather a long InChI. We can also apply InChIs to molecules of current interest. Remdesivir is a promising compound for treating COVID-19. It has this particular structure, and its IUPAC name is given here, not the easiest thing to pronounce. There are non-IUPAC naming systems which would give you different names for this molecule. If you look at this name, then IUPAC obviously thinks that this molecule is basically alanine. If you look at this part of the molecule, here's an alanine molecule, and all the rest of it is just extraneous bits added on to the core alanine molecule. So the structure of the name, just to represent the whole system, focuses you on a particular part of the molecule. But actually, the person who drew this structure wasn't thinking about this being an alanine derivative. They were thinking about the tetrahydrofuran in the middle. Looks very much like a fragment of RNA. They were thinking of this as being an RNA analog, which might possibly inhibit viral replication, which is how remdesivir may well work. So by drawing it, they were emphasizing one part of the molecule. By naming it in a standard way, you're emphasizing a different part of the molecule. Perhaps what this molecule does is completely different, and one shouldn't be too distracted by the names. One can always also give it a CAS number. This is the first number here is very large, which shows it's been registered quite recently. One can give it a SMILE string. All these ats refer to the stereochemistry of the SMILE string. Or it can be given an InChI, which also defines the stereochemistry in quite a lot of detail, or an InChI key. This is a way of compressing the InChI data into a shorter string. And this shorter string, always exactly the same length, is another representation of the molecule. Notice here, it doesn't finish Ufer-Häuser, as the ones we've seen before does, but Weiss-Sorbdza, which means there is stereochemistry in this particular molecule. So these names are useful for storing, for searching. If you put them in a patent, you can see if you've got the same molecule as anyone else has. But they're also useful on a simpler level, just working out if you're drawing the molecule correctly. This is a mol file. This is two-dimensional information about the molecule, which we can draw in lots of different ways. So a huge number of different mol files will represent the same molecule. But this is a different two-dimensional representation of the same thing. this is drawn emphasizing its likeness to RNA. This is drawn in an extended form, which might be more familiar to a synthetic chemist. And these two representations should represent the same thing. The heterocycle at the end has just been turned over, but that looks the same. Here, the carbon-nitrogen triple bond has been used, given the standard abbreviation CN. The stereochemistry here is pointing up, but it's been turned over pointing down. If you look carefully along this, the chain, then this molecule is exactly the same as this molecule, and therefore it should have the same InChI and the same InChI key. But actually the InChI key for this is this unpronounceable name, and the InChI key for this is this unpronounceable name. Now the first half of the InChI key is the same in both cases, which tells us it has the same connectivity, but the second half is different, which tells you it has different stereochemistry. And that's confusing because it looks very much as if it has the same stereochemistry. So when I first drew this, I was confused by it until I realized this is actually part of the algorithm. And I was using the algorithm in ChemDraw, but you can use the InChI algorithm in lots of different ways. InChI wasn't quite clear what CN meant and what PHO meant instead of drawing a phenyl ring joined to an oxygen explicitly. So it decided that the stereocenter here and the stereogenic center here were not defined as I'd intended, but they were undefined. So the understanding of this structure, even though it appears to be drawn in an unambiguous way, is that two key stereocenters are regarded as undefined, and that's much less likely to cure COVID-19. We need this second section of the InChI key is different, so the stereochemistry is different, and the ChemDraw to InChI conversion didn't interpret this in quite the same way that I had, and that could have enormous consequences. If you're selling a compound, if you're trying to make a compound, you need to know exactly what it is. And generating the InChI keys of different representations can warn you of different possible errors. If we redraw the structure like this, drawing the cyanide in full, drawing pH bond O instead of PHO, then ChemDraw interprets it in the correct way, and this structure and this structure are given the same InChI key. But it shows how very subtle changes in representation can lead to a completely different molecule. And in this case, it would be a molecule with completely different biological properties, because the stereogenic center at this position is definitely really important for the activity of remdesivir. So naming things is really important, and we have to do it carefully. Both SMILES and InChI provide text-based descriptions, but if we really want to have just one name for a structure and just one structure for a name, InChI provides an algorithm to do this. When I say InChI is better, then a number of people will regard this as being fighting talk, because they regard, there's clearly an argument that SMILES is a different but extremely useful representation. So why is InChI better? It is better because you can be sure, or much more sure, that a single structure will give you a particular name, and that name will give you the single structure. So if two different people make the same molecule in different parts of the world, they can create the same InChI and know that they are creating the same InChI as each other without communicating with each other. That's not true for a Cas number, for which you have to consult Cas, and for SMILES, there are different ways of deciding what is the preferred SMILES string. So they might come up with different SMILES, but they should only come up with one InChI. And that's a key advantage of the InChI. The InChI is really useful because it is canonical, but it's successful not because of the underlying design, but because people use it. People find the InChI to be useful, and so they use it not because they're obliged to, but because it helps them with problems that they have. The InChI has been explained in an infographic kindly provided by Springer. The InChI is a unique identifier of the chemical structure, which you can use as its digital signature, developed by IUPAC and the InChI Trust. The purpose of the InChI is to streamline naming conventions, to uniquely identify a chemical substance, and to assist in merging and linking chemical databases. It's really useful for all three of these things. It seems to me that if it's useful for other things too, then it should be used for other things too. The InChI is useful for everything that people can find to use it for, rather than just things for which it was designed. But again, there are differences of opinion here. Should you insist that InChIs should only be used as identifiers, or should you use them whenever for any purpose for which you might find them useful? And it's the only structural representation which is in the public domain, open source, and freely available. It's been developed for about 20 years now, since Steve Heller and Steve Stein initiated the project. It has been, various versions of the InChI have now been released. They're all available on the InChI Trust website, and the InChI project is ongoing. It's continuing to develop continuing to expand its coverage to new areas of chemistry. But since the beginning, it's been able to cover nearly all organic compounds. Here are some more examples of InChIs. So methanol, CH4O, we can see here. So the molecular formula of methanol, which for methanol is probably all you really need. And the InChI key for methanol is much longer than methanol itself. But again, we see Ufa-Oiser. This shows it's got no stereochemistry. Lithium hydride, we can use InChIs for organometallics, though not for all organometallics. Or we can use it for more familiar molecules like acetone. All of these are Ufa-Oiser molecules because they have no stereochemistry. We can use the InChI software in many ways, and we can learn more about it from the InChI Trust website, and we can download it from the InChI Trust website. It's been tested in PubChem. Actually, 90 million, I think, is an underestimate of the number of chemical compounds for which they have generated InChIs. If you're handling a database with tens of millions of entries, then finding out if you have a duplicate or not is really very, very difficult. But if you just create the InChI for all of them, then you can find out much more easily whether you have duplicates, whether molecules which look similar are actually the same or not. And in generating tens of millions of InChIs is also a really good test of just how effective the InChI is. And in very nearly every case, the InChI has provided a good representation of tens of millions of molecules. So how does the InChI work? Well, here is a familiar molecule. This is caffeine. But how does the InChI describe it? The InChI is deliberately designed to have a series of layers. So if we look at the InChI for caffeine, it begins by telling us it's an InChI and version 1S, the standard version of the InChI. We then have the molecular formula, which is written in the Hill order, that is carbon, then hydrogen, and then the elements alphabetically. We then have the connectivity, which tells us how these different atoms are joined together. So atom 1 is connected to atom 10, to atom 4, to atom 9, to atom 6. Since we only have 8 carbon atoms, atom 9 must be a nitrogen. We don't number the hydrogens. So if you look at this for a while, you can work out what the numbers should be. So atom 1 is this methyl group, atom 2 is this methyl group, atom 3 is this methyl group, then atom 4 is the only carbon with 1 hydrogen on. The other carbons in this particular structure don't have any hydrogens on. And a key part of constructing an InChI is deciding on a unique numbering system. How do you decide which of these methyl groups should be labeled 1, which should be 2, and which should be 3? You have to be able to do that from the structure and from nothing else. That's actually a really difficult problem. And this is something which Dmitry solved in writing the original version of the InChI to create a unique numbering system algorithmically from the structure. If you can't do that, you can't create unique naming systems for molecules. So you can see the beginning of the algorithm here, though not all of the detail, in that more hydrogens means you have lower numbers. So the 3 methyl groups are carbons 1, 2, 3. Then carbon 4 is the one with 1 hydrogen on, and the others are carbons with no hydrogens on. But the reason why this is 1 and not 2 or 3 is rather more subtle. So this layer describes the connectivity, and then the final layer describes where the hydrogens are. And we'll come back to that later because this is a really important issue. But this is the InChI for caffeine, and there's only one way of numbering it, by the InChI algorithm. Here is a more complicated InChI, more complicated because this is a molecule with stereochemistry. So the InChI begins in the same way, with the layer with the molecular formula, the layer with the connectivity, but now we have an extra layer marked P because there is a charge. This has a positive charge of +1. So the charge layer says there's a charge of +1. We have stereochemistry here. So T1 minus M1 S1. We actually have 3 layers to describe a single stereogenic center. And that might sound rather excessive, but we want to be able to describe relative stereochemistry as well as absolute stereochemistry. We want to be able to relate this to the representation. So it turns out that having 3 layers to describe stereochemistry gives more flexibility than simply listing whether each stereocenter is up or down. In this particular example, there's a non-standard isotope, so we need to use the isotope layer. And here we're saying the hydrogens are in particular places. We want to say that a hydrogen is on the nitrogen, so this is NH3+, rather than say having a hydrogen on the oxygen here. So the positive charge would be put on the whole molecule. So the charge is a property of the molecule as a whole, not of particular atoms within it. But this layer structure shows one part of the power of the InChI representation. Because if we were to leave out the layers at the end, we'd still be, we'd be losing some information, but we'd still have much of the structure left. So if we leave everything out from /T onwards, we would have the same molecule. We'd have lost the information about the stereochemistry, but we still know the molecular formula, we still know the conductivity, we still know that it had a positive charge. So parts of InChIs provide useful information about what's going on. And that's particularly useful for thinking about stereochemistry, because if we have a molecule which is presumably racemic, or one which has a defined stereogenic center, their InChIs are exactly the same, or at least the beginning of the InChI is exactly the same. The only difference is the one with the defined stereogenic center has extra layers defining what the stereogenic center is. So this is a convenient way of encoding molecules. Suppose you want to look in a database for this structure and include the different enantiomers. Well, you just look to the beginning of the InChI and ignore the last bit, and then you'd be able to find both a single enantiomer and racemic mixtures and the enantiomer of the thing you were looking at. There are many peculiar molecules in the world. These are examples of molecules called Munchknones, which you can't write without having a negative and a positive charge. These are molecules which exist and can be isolated, but is the best way to write them like this, negative charge on the oxygen and the nitrogen? Or is it better to write it like this with a negative charge on the carbon and on the nitrogen? None of these are exact representations. They're all representing the same single molecule with delocalized electrons. But because the InChI doesn't define where the charge is, we have the same InChI for all of these structures. So if you draw the structure, you might draw several different things. It might not be obvious they are in fact the same, but the InChI allows you to unite the different representations. Tautomerism is also an issue. An amide, of course, is a very familiar molecule, and this is the InChI for acetamide. C2H5NO, here is the connectivity. And the hydrogens, well, actually, are both the hydrogens going to be on the nitrogen, or is it going to be in the immanol form with a hydrogen here and a hydrogen here? Well, by default, the InChI doesn't do what you might expect. And if you're thinking about mass spectrometry, this doesn't really matter. But to represent an amide in this form is a slightly non-standard way of thinking about molecules. So InChIs don't necessarily pin down the position of a hydrogen unless you ask them to. And this can be useful if we think about DNA bases, for example. is this the correct representation, or should the hydrogen be here, or should the hydrogen be here, or should the hydrogen be here? These are all probably the same molecule. They all have the same standard InChI. Well, when I say they're the same molecule, as I've drawn them, they're different structures because the hydrogens are in different places. But if you were to put them in water, you wouldn't be able to distinguish them or separate them. So maybe they are the same molecule. And this comes back to a philosophical question of what is it that we mean by a molecule? If we have a bottle with this molecule in, then all four of these things would be the same. We wouldn't be able to distinguish them or separate them. If we're thinking about an isolated molecule in the gas phase, then maybe they are different. So where should the InChI draw the line? Should the InChI say that however you want to draw it, that's what will be encoded? Because that would mean different people would make different representations of the same thing. They'd have different InChIs for molecules which are probably the same. Or should we be a bit laxer and say, we just don't care about hydrogens at all? Then molecules which probably are importantly different would be given the same InChI. So this is a really interesting and difficult fuzziness. How do we define what a molecule is? And the decision that the InChI has made is that these molecules are all the same, they allow the protons to move around, but most tautomers are not the same. Now, this is currently a discussion within the InChI subcommittee. Where should we draw the line? When are things the same and when are they different? One ongoing InChI project is to work out what we should do if we consider all tautomers to be the same. And this is totally convenient because it means that we won't be thinking two molecules are different when you have a bottle of them, they're indistinguishable. But it also means that some molecules people might want to distinguish as part of a reaction mechanism, for example, are given the same InChI. So where should we draw the line? We are still thinking about this, and if you have any views, then do let me know. The InChI is almost perfect. One of its minor issues, or major issues if you're interested in spiroacetals like this, is that it misses this stereocenter. The InChI algorithm is very good at finding stereogenic centers, but it misses a very small number of examples. So the InChI will represent a wide number of molecules. The InChI key is useful because it condenses an InChI into a string of letters which is always exactly the same length, always 25 characters long. This makes it much easier to store in a database with fixed length fields. It makes it much easier to ask Google or other search engines to search for an InChI. And an InChI can be of arbitrary lengths, and for a very large molecule can be very long. An InChI key is always guaranteed to be 25 characters long. The first section of the InChI key gives you the connectivity. The second section gives you the stereochemistry and additional flags. And the final letter is a check digit. So the InChI key for caffeine is this. U for Euser tells you it doesn't have any stereochemistry, but it's very difficult to go from this string of letters back to caffeine unless you happen to know the answer. Of course, it's possible then that there'll be collisions between InChI keys. And about 10 years ago, people were saying, well, it's very unlikely we'd ever find one because collisions are really very, very rare. And collisions are very rare. So in 2009, it was pointed out that no collision has ever been reported. So maybe we won't have to worry for 100 years or for 1,000 years. I went to a conference shortly after this where I talked about spongistatin, which is an antimitotic macrolide, a really very interesting molecule with this InChI key. And it's got a large number of stereogenic centers. So we can write down molecules which are not the same as spongistatin, but with the same connectivity. So neither of these molecules are spongistatin. They differ in the stereogenic centers. The InChI key for the first one is this, and the InChI key for the second one is exactly the same. So this was the first reported result of InChI keys, of a clash of InChI keys for a molecule which is actually a natural product, a large molecule, but not an impossibly large one. Of course, you could say this is cheating because this is keeping the first half of the InChI the same by design. So this isn't an InChI key clash in terms of different structure, but these two molecules also have exactly the same InChI key. So InChI keys can clash, but very, very rarely. If InChI keys are different, you can be sure two molecules are different. If they're the same, it's worth checking the InChI, but you can be reasonably confident they're going to be the same. And as I said before, InChIs are successful because people can use them. Molecules can be represented in lots of different ways, and this is taking away data by encoding a molecule as a two-dimensional structure, or as a mol file, or as a three-dimensional structure, or as an InChI, or as a SMILES. All of these can then be encoded in further ways. The InChI can go to an InChI key. This is an irreversible process. Two-dimensional structure can be turned into fingerprints, as can a mol file. These also are irreversible processes. You can get a Cas number from a chemical name, provided you make a contribution to the chemical abstract service, if you're doing this for the right, if you want to handle the Cas numbers afterwards. So these are all ways of encoding molecules, but these are all simplification of molecules, because molecules also have three-dimensional structure, they have conformations, they have movement, they have reactivity. We can use the InChI as an identifier for this, but not as a way to describe it completely. So that's how the InChI works. This is the center of this target of InChI applications. The InChI works very well for most molecules. Tautomers are under discussion at the moment. Organometallics, it can't cope with all organometallics, but very soon we hope a project will be finished which will enable it to describe all organometallics, or nearly all organometallics. Stereochemistry, InChI describes stereochemistry well, but there are complexities of advanced stereochemistry which it can't yet describe. Suppose you have a molecule which has two different groups of stereocenters, where you know their relative orientation with respect to each other, but not between the two groups. This is a real problem in natural product identification, but one which at the moment the InChI can't describe. All of these InChIs can be described by InChI keys, and then it's possible to build InChIs, applications using the InChI and the InChI key to do more things. One of them, I mentioned for Jeremy Frey, in case he's listening, is the QR InChI. Can you take an InChI, put it into a QR code? Well, this would be really useful if you're wandering around your chemical store cupboard, you see a bottle, you're not quite sure what's in it, or you're not quite sure if you're interpreting the name correctly. Just point your smartphone at a QR code in a standardized form for an InChI, and this will take away your headache. We hope that fairly soon it will be possible to have a standard QR InChI, so everyone will know exactly, there'll be just one QR InChI, which is appropriate for each molecule. So this would build on the InChI standard in a way which would make it even more useful. Other things that we might worry about, can we look at reactions? We've looked at molecules, can we use InChIs to encode reactions? Well, yes, we can do that too. And encoding reactions might be a very useful thing to be able to do, because at the moment, if you are searching for reactions, you have to go to the publishers who are available to help. IUPAC contributes to worldwide understanding, the ACS advances the broader chemistry enterprise for the benefit of the Earth and its people, and the RSC helps shape the future of the chemical sciences for the benefit of science and humanity. But once you've published a paper with these publishers or with commercial publishers, then do you still own your data? Can you put it in a way which other people will be able to find? At the moment, we tend to rely on secondary publishers, such as the Chemical Abstract Service or Reaxys or other resources, which allow us to search for molecules and search for reactions within publications. If we had an identifier that would mean we could search directly, then we would make chemical information much more accessible. The InChI does that for molecules, and we're developing ways of doing this for reactions as well as for molecules. So synthetic chemists want good data, they want it to be accessible, comprehensive and reliable, and we want it to be open access to be consistent with our funders' requirements, but also to mean that the chemistry that we discover can be as accessible and as widely used as possible. The InChI provides a way of making data more accessible. So the InChI describes molecules. It describes a huge range of molecules in a way which is unique, in a way which is tractable, in a way which is open source and available. It can be extended towards reactions, mixtures, polymers, big molecules. We're developing a large number of teaching resources so that it's possible to use these in undergraduate courses. And all of these provides a tool to make chemistry data more easy to find and to make chemistry more accessible. So the InChI is a very useful way of measuring molecules, and I would urge you all to consider using it in handling your chemical data. So I would like to thank Jeremy and Sammy for the invitation, and to thank you all for your attention. And I'd be happy to answer any questions.